Hello and welcome back. In this video, we are going to look at eigen means special values and eigen, again repeating myself, special vectors. And uh, these are important ideas in linear algebra and neural networks. So if these are confusing right now, it is perfectly okay, because by the end of this video you'll completely understand, or at least have a good intuition about what these mean and how these relate to uh, uh, thinking about neural networks. So in the past several videos we have looked at linear transformation, and in linear transformation, we always said that there is some matrix A that we can think of a machine. What it does is it takes input vector and it sends it out uh, to another vector, say y, that this is in a different space and this is in a different space. But when we talk about eigenvectors, it makes sense when a transformation maps a space back to itself. So in this video we are going to say that this particular uh, machine or the matrix that does something to an input vector, stretches it, shears it, it does so and outputs it in the same space. And so to write it mathematically, we would say that A colon x, and then we put an arrow and then say x. This means A takes an input vector and outputs another vector in the same world, if you mean it. Now, for linear transformation, A, let's say if we are trying to do a transformation, right? So let's say A is a matrix, and we say that the A matrix has these values. So any linear transformation can be represented as a matrix, and this matrix tells us how much the transformation pushes the vectors around. For example, if we plug in the value of x is equal to 1 0 in this particular machine, if you call it, or in this transformation matrix, here is what will happen. If we dot those two, we have 2 1 1 3, and if I dot that with 1 0, what we get is the following: 2 times 1 plus 1 times 0, then the bottom line 1 times 1 plus 3 times 0, and we get an output vector which is 2, and the bottom down here we have 1. So the vector rotates a bit and gets stretched. How do we know that? We can go ahead and plot it. So let me get an arrow. Let's say we have this space, that's our x-axis, and this is our y-axis, and on this we are going to plot the values. So let's say we have the values for let's say this is 1 on the x-axis, this is 2 right here, this is 1 on the y-axis, and here we have 2. So the very first point that we have on this plot, let's say the input vector that we had, or the input data point we had, was 1 0. So x-axis 1, y-axis 0, it would be this point. And so what essentially we are trying to input to this particular machine or transformation matrix is this vector, which is x, and we are it has the coordinates 1 0, and we say that that's the vector x. What happens when we transform the vector? When we transform the vector, it its new coordinates are 2 1, so x-axis 2, y-axis 1, so it comes around there. So let's plot that in a different color. Let's say this one, 2 1, so we are right here. And so if you see, what has happened is the following: this this particular transformation matrix, what it did was, as we input a vector x, which was 1 0, and when it output we get another vector which is again in this case, let's say, is in the same space. It is 2 1. So we went from this blue arrow to that arrow, and that's what that's what transformation does. So most directions behave like this. So we got some rotation, we got some stretching, and so these are sort of mixed direction. But now here is an interesting or magical thing that can happen. Can we ask a question? Are there any directions that the matrix does not rotate? Imagine that. Is there a vector, let's say, let's call that vector z, and we what we are asking is there a vector z such that when you apply a, it points in the same direction as before? So if we have a vector, let's say if this is a coordinate, if we have vector z like this, after we apply the transformation, it still points in the same direction, and not necessarily it will have the same length, but it would have the same direction. So let's say the new vector would be something like this, or it could be something like this, right? Z prime. And this special condition is a z is equal to lambda z, and here this z that we are writing, or z, is the eigen vector, or as I said earlier, this is, you can think of, is a special vector, and this lambda right here is called as the eigen value. I think the eigen word is comes from the German language, so eigen value, or this is a special value. And so this transformation matrix gets us an eigenvector that is a direction unchanged by this transformation, an eigenvalue which tells us how much it stretches or shrinks in that direction. Now, if you ask me, well, Nilesh, why does it matter? Why do eigenvectors matter? Why do you care about them so much? So let's switch to an analogy, and this is where I was talking about a wind in a room sort of analogy. Imagine a room, and I'm just going to draw something that is just going to, I don't know if it will help, but let's try that. So let's say we have a room, and sorry, I'm trying to get the colors right. So we are in a room, let's say, and I'm trying my best to draw it. So that's where we are, and let's say there is some wind inside of this room, going like this, and let's say we release a paper plane inside of this room, and I'm going to show that here. So let's say we release a paper plane in this room, and it tries to fly in this room. So most orientations would be something like this. It will rotate the plane, the wind can change the direction, push it on the side. But imagine there are some special orientations, like if you point the plane in that direction, the wind pushes it either wind pushes it either forward, straight forward, or uh, backward, right? Let's say most forward it will be positive values, so forward, but it doesn't uh, rotate it or doesn't move it sideways. It just scales the vectors, and the directions in which this would happen is would be the eigen vectors, and the strength of the push in that direction, we can think of it as the eigen value. So eigenvectors in this analogy of wind that we have can be thought of as wind aligned directions, and eigenvalues could be the strength of the wind along those directions. So what we are going to do is we are going to look at this wind from a different uh, set of axes, where even though the wind hasn't changed, it's the same wind, but we are changing orientation. And why do we do that? Because it will help us um, align to an axis that helps us make calculations easier and make sense of the wind mathematically easier. So that's sort of the intuition I wanted to give, and hopefully it will get clear as we dive further into some of the math in this video. Now, if you're wondering what, how do we find the eigenvalues and eigenvectors, here is how we can do that. So, to find the eigenvalues or eigenvectors, we start out with the equation A z, or let's write it as A z is equal to lambda z. And what we do now is bring the terms to one side, and so we can write A minus lambda I is equal to z is equal to 0. And you're wondering how the I came. I is just an identity matrix. So for non-zero z to exist, the matrix A minus lambda I, it must be singular. That is, its determinant must be equal to 0. So what I mean by that is, if we get the determinant of A minus lambda times I, it needs to be 0. And this equation gets us the eigen values. So let's imagine the machine or the matrix that we talked about earlier, which is A is equal to 2 1 1 3, and we can compute the values for A minus lambda I as follows. This would be 2 1 1 3 minus lambda into I would be just 0 1 1 0 0 1, and so what we get is 2, this would be 2 1 1 3, and if you multiply values here, it's just going to be lambda 0 lambda, and this would be 0 lambda. And if we perform the subtraction, we get values of 2 minus lambda 1 1 and 3 minus lambda. So these are the values for A minus lambda I. What we do next is calculate the determinant of this. So the determinant of A minus lambda I is going to be equal to this term multiplied by this term minus uh, this one multiplied by the other one. And so that comes out to 2 times 3 is 6 minus 2 lambda minus 3 lambda plus lambda square minus 1. And so what we get is lambda square minus 5 lambda plus 5. And as we said earlier, we can equate it to 0. So the equation that we are now looking at, if we bring this here, is lambda square minus 5 lambda plus 5 is equal to 0. If we try and solve this using a quadratic formula, we would get something like this. Lambda is equal to 5 plus minus square root of 25 minus 20 divided by 2, and that gets us 5 plus minus square root of 5 divided by 2. And if you go ahead and calculate this, I've done this already, what we get are two values for lambda. So lambda 1 is approximately equal to 3.61, and lambda 2 is approximately equal to 1, let's write that clearly, 1.38. And so these are the eigen values that we have calculated. We can now use these eigenvalues to get our eigenvectors or special vectors. And to do that, we go back to the relation that we had earlier, which is A minus lambda I times Z is equal to 0. And we plug in the values for lambda to get the value. So first we use lambda 1. So for with lambda 1, let's change the colors here. So let's say we use the lambda 1, and with lambda 1, which is 3.61, here is what we would get. This would be, this is, where is the equation? We have this one, a minus lambda. So this would be 2 minus 3.61, 113 minus 3.61 times z or z is equal to 0. And if we perform this subtraction, we should get 1.61811, and this would be 0.618. And you can check the calculations, it should be the same. So what this gets us is uh, value for z1 and z2. So if you look at z1, this would be something like minus 0.52 and 0.85. So these are the values for z1. So that's our first eigenvector that is corresponds to the eigenvalue of lambda 1. And if you calculate the same thing for the lambda 2, I've already done that. I'll directly write the vector. It comes out to z2 would come out to minus 0.85, 0.52. So this would be the second eigenvector, which is paired with the eigenvalue of lambda 2. So these two eigenvectors, they are orthogonal. So if you get a dot product of z1 with z2, it should be 0, and they form a perfect new coordinate system. If we look through that coordinate system, we can then describe the wind aligned directions more easily, the wind that we talked about a few minutes earlier. Now, when we take these eigenvectors z1, z2 and use them as new axes, something amazing happens. The matrix A, let's done here, the matrix A that we have, which is this one, uh, which used to rotate, mix, and stretch the vectors, suddenly it becomes like this. I'm going to show it with this capital lambda. It will become like this. This is the meaning of this matrix lambda. So lambda is equal to z inverse a z. And what it tells us is if we change the coordinate system to eigenvector axis, then the transformation A right here just becomes pure stretching and no rotation. So stretching only and no rotation. And so no rotation. And why? Because only the diagonal terms are there, off diagonal terms are all 0. So the wind did not change any direction. So what we did was we changed the orientation of our coordinate axis to look at the wind. So this is one of the most important geometric facts in all of the linear algebra. Before we end this video, let's look at a slightly bigger 3 by 3 matrix with off diagonal values, and hopefully it will help you clearly see what A looks like when it's in a messy mixed form. How do the eigenvectors untangle this transformation, and how does the lambda matrix become diagonal, and how ultimately we can also go get back our A using the relation, let's say A is equal to Z inverse. So how it compresses the entire transformation into simple stretching along special directions. And just really quickly, why these two are correct is, let's say if we start out with, let me move the screen up. If we start with A is equal to Z lambda Z inverse, if we multiply both sides by Z inverse, so what we get is Z inverse A, sorry, Z inverse A is equal to Z is equal to lambda, so lambda Z inverse, because that Z would get cancelled out, and so now we multiply both sides with the Z. So what we get is Z inverse A Z is equal to is equal to lambda. So that's a very pretty straightforward. Let's now begin looking at a full 3 by 3 matrix and how we can calculate the eigenvalues, eigenvectors, and also look at the lambda matrix, and how we can get the diagonal matrix. So the matrix A, or the machine that we said earlier that does the transformations for us, is as follows: 2 1 0 1 2 0 and 0 0 3. As you can see, the off diagonal terms in this last row are zeros, so we just have this top left block which does the stretching, because stretching or transformation of matrix other than stretching based on the off diagonal values we have. So the first thing we'll do is put it in the form A minus lambda I, and that would be equal to 2 minus lambda 1 0 1 2 minus lambda 0 0 0 3 minus lambda. Next thing we need to do is compute the determinant of this matrix, and to do that we need to calculate three terms. So the first term is going to be with C11, or we can say for this part right here. First row, so C11, let me put it this way. C11, we are going to look at 2 minus lambda, which is, we're going to look at that, 0 and 0 3 minus lambda. So what we get, if we multiply the diagonal terms, we get 2 minus lambda 3 minus lambda minus 0. That gets us right here, 2 minus lambda times 3 minus lambda. Then we calculate the term C12, which is 1 0 and then 0 3 minus lambda. So 1 0 and then 0 3 minus lambda, and so what we get is the following: 1 times 3 minus lambda minus 0 is equal to 3 minus lambda. And the third term is C13, and that's going to be equal to, let's write that down, 1 2 minus lambda and 0 0. So here we get 1 times 0 minus 2 minus lambda times 0. So this essentially is just 0. Now we can sum these three. So what we can say is we can take this one, and this is just 0. So what we get is the following: determinant of A minus lambda I is equal to 2 minus lambda 3 minus lambda minus 3 minus lambda plus 0, and that gets us the if we factor out 3 minus lambda here, what is left inside is 2 minus lambda minus 1. So we get 3 minus lambda 1 minus lambda, and this looks too short, and that means we lost a factor. So let's catch it. We must remember that the lower right element also contributes to another 3 minus lambda, because we effectively dropped him. when expanding only the first row. So the full determinant factor would be as follows: determinant A minus lambda I is equal to 3 minus lambda in brackets square brackets 2 minus lambda minus 1. And so if we expand the 2, let's take the 2 minus lambda square, expand it, what we minus 1. If we expand it, we get 4 minus 4 lambda plus lambda square minus 1, that is equal to lambda square minus 4 lambda plus 3. And so going for plugging that back in, what we get is the determinant A minus lambda I is equal to 3 minus lambda times lambda square minus 4 lambda plus 3, and that is equal to 3 minus lambda. So if you try to get the factors for this, we would get lambda minus 1, lambda minus 3. And so the values we have is lambda 1 is equal to 1, lambda 2 is equal to 3, lambda 3 is equal to 3 as well. So these are our eigenvalues for this setup. Now to find the eigenvectors, here is what we can do is we know that a minus I is equal to a minus lambda I times z is equal to 0. And so what we can do is just plug in the values of lambda. So the first case, lambda 1 is equal to 0. Sorry, lambda 1 is equal to 1. So we say a minus I z is equal to 0. So the A matrix that we have, A is so we have A as 2 1 0 1 2 0. Let me just check that again. All right, so we have A is 2 1 0 1 2 0 and 0 0. I think 2 1 0 1 2 0 and 0 0 3 0 0 3 minus minus I, which is just 1 1 1 0 0 0 0 0 0, and this subtraction after subtraction, we have the z, which is the three axis coordinates. Let's say that's x y z, and we set that equal to 0. So if you perform the subtraction in here, what we get is 2 minus 1 is 1, 1 minus 0 is 1, 0 minus 0 is 0, and so on. Here we have 1 minus 0, 2 minus 1, 0 minus 0, and the same thing here. So we have 0 0 and 2 times x y z is equal to 0. So what this gives us is the following. We have this is x plus y is equal to 0. That's what we get for the first two, and the last one we just simply have 2z or z is equal to 0. That is essentially telling us that z is equal to 0, and this is telling us that y is equal to minus x. And so if we choose x is equal to 1, then here is the z1 that we have. Z1 would be equal to 1 minus 1 0, and that's our eigenvector, which has the eigen value attached to it, which is lambda is equal to 1. Now similarly, we can find the eigenvector for lambda is equal to 3, and in this case we have the relation as a is equal to a minus 3I times z is equal to 0, and if we again take the matrix A, which is 2 1 0 1 2 0 0 0 3 minus minus 3 3 3 is 0 0 0 0 0 0, then z is equal to 0. So if we solve this, we get minus 1 1 0 1 minus 1 0, and then this is 0 0 0. X y z is equal to 0. So in this case, the equations that we have are minus x plus y is equal to 0, x minus y is equal to 0, and the last one is just 0 is equal to 0. And so from these two, what we can get is y is equal to x. And so we can say that there are two independent eigenvectors from this that result from this. One is, let's call this z2. This is 1 1 0, and the other one is z3, that is 0 0 1. And that's if we assume the value of x as 1. So y x is 1, y becomes 1, z is 0. And in the other case, we assume x is equal to 0, and so here we assume x is equal to 0, z is equal to 1. Here we assume x is equal to 1, z is equal to 0, and we can do that because in this particular example, x we are saying that x is free and z is also free. Y because we have y is equal to x, and we get this 0 is equal to 0 right there. So with that calculated, what we can do next is build our matrix for z. That is the eigenvectors and the matrix for eigenvalues. So let's do that. Choose a different color. Let's say this one. So our z then becomes the following. We have 1 minus 1 0, that is this matrix we had, and then we put the other two the vector we had, and then we put the other two vectors 1 1 0, which is this one, and 0 0 1, which is the last one, this one. And likewise we get the lambda matrix, and for lambda matrix the diagonal, so we have the diagonal terms which we need to plug in, and then these off diagonal values, they are going to remain 0. So the diagonal values that we have, lambda 1 that we saw, so we have the values 1 3 3, that's exactly what we are going to write here, 1 3 3. So this is the big this is the big sort of the findings of all the calculations that we have done. We have set of, so each column is a eigenvector, and associated with that vector is a specific eigenvalue that's right on the in this particular matrix. Now if we want to go back and try and see how uh, these are related to the matrix A that we started out with, here is what we can do, and we can say that this top left block, which is right here, that's let's call that B is equal to 1 1 minus 1 1, and if we get the determinant of that block B, we get 1 times 1 minus 1 times minus 1, that equals 2, If we get the inverse of this, b inverse, I've already calculated that. If you haven't, we simply swap these. So 1, it still stays 1 1. We swap the values, signs on the off diagonal terms. So this becomes plus 1, and this calculates to 1 half minus 1 half, 1 half, and 1 half. And we plug this back into the z inverse to get the z inverse. So z inverse is going to be equal to, this is 1 half minus 1 half 0, this is 1 half 1 half 0, this is 0 0 1. And why this was possible? Just because these off diagonal terms in the bottom last row and the last column are 0, therefore this was sort of a shortcut. Once we have the values for z inverse, we can now verify if the a we can verify if a is equal to z lambda z inverse. So let's do that. We first calculate the value for these two. So the z that we have is 1 minus 1 0 1 1 0 0 0 1, and the lambda that we have is 1 0 0 0 3 0 0 0 3. And if we get the dot product, we essentially take this row, this column, and so on. So here is what we get. The first row, we have 1 times 1, 1 times 1 plus the rest 2 would be 0, plus 0 plus 0. Then for the second position, we have 0 plus 1 times 3 plus 0, and then we have 0 plus 0 plus 0, because we have 0 times 3. And likewise in this case, we have minus 1 times 1 plus minus 1 times 1 plus 0 plus 0, and then we have 0 plus 1 times 3 plus 0, and then finally we have 0 plus 0 plus 0, the 0 plus 0 plus 0, and then we get 0 plus 0, because this times 0 is 0, this times 0, 0 times 0, 1 is 0, 0 times 0 is 0, 1 times 0 is also 0. And likewise we get 0 plus 0 plus 0 again, and then finally we have 0 plus 0 plus this is 1, so 0 plus 0, 1 times 3. And so finally, if we look at the values, we get 1, this is 1, this is 3, this is 0, and then here we have minus 1. Looks like I made a mistake somewhere. So this we are getting this as minus 1. So let me write that down. I'll look into that in a moment. And then we have this is 3, this is 0, then this is 0, 0, and 3. All right, so just to remind myself, this was what we are trying to calculate is ZA and not the A. So that's the part we have. Next, we keep going. We then take this and multiply it with the Z inverse. So we have the Z lambda, we dot it with the Z inverse. So we have this matrix 3 0 minus 1 3 0 0 0 3, and the Z inverse is 1 half minus 1 half 0 1 half 1 half 0 0 0 1. And again, if you go through the calculations, let's do that. This is 1 times 1 half plus 3 times 1 half plus 0, and then we have 1 1 times minus 1 half uh, plus 3 times 1 half plus 0, and then the next one is just 0 times 0. The next one is just all would be 0. And in the following line, we have minus 1 times 1 half plus 3 times 1 half plus 0, and then we have minus minus plus, so 1 minus 1 times minus 1 half plus 3 times 1 half plus 0, and then this one is 0. In the last row we have 0 0, so this is just going to be 0. Again, this would be just be 0, and the last part, this is just going to be 0 0 plus 0 plus 0 plus 3. And if we get the calculations right, we should get our original A matrix back. 1 plus this, so this is going to be 4 by 2, and so that's just 2. This is going to be 2 by 2, so that will be just 1. Then we have the 0. This would be 3 minus 1, so that's 2 by 2 again, just 1. And here we have minus minus plus, so 3 plus 1, 4 by 2, which is just 2. This is 0, these two are zeros, and this is 3. Awesome. So finally what we did was we calculated this, and this is exactly equal to A. So this is we can write this is equal to A, and that's the diagonalization is now complete. So what has happened here is the original matrix A, it pushes the vectors in messy mixed directions in the xy plane, and then eigenvectors, they tell us the wind aligned axis where A does not rotate the vectors. So eigenvalues tell us how much A stretches these directions. And in the eigenvector basis Z, that is, if we look instead of using the regular axis, let's say we use the eigenvector axis or basis, then A becomes purely scaling question using the matrix lambda, because instead of using this matrix for as a machine, what we are doing then is using this matrix as a machine. And you see that all the off diagonal terms in this machine or matrix are 0, and so the only way this matrix can affect a vector is by stretching, and that's these diagonal values. And uh, that's why it makes calculations easier. So if we are looking at a messy data, and so this relation, which is A is equal to Z lambda Z inverse, it's one of the most important equations in linear algebra. So it helps us look at a messy data rather than using a messy matrix A. If we view it through lambda matrix, it makes it look easier. So the key takeaway points from this particular video are that eigenvectors or the special vectors are special directions. They are the special directions in a linear transform that does not rotate, right? It does not rotate. And eigenvalues against are special values. They tell us how much stretching happens along those directions, which the eigenvectors define. And these are used in uh, PCA. So in PCA, this A that we have, this would be a covariance matrix. And so covariance matrices give PCA directions using these eigenvectors. Rotation matrices. So those tell why sometimes there are no real eigenvectors. And in all of this relation Z inverse A Z is equal to lambda, or the other way around right here, this is sort of the heart of diagonalization in this relation. And if you think about the wind analogy again, eigenvectors are the wind aligned orientations of your paper plane. If you enjoyed this deep, beginner friendly walkthrough, eigenvalues and eigenvectors, hit like, subscribe, and drop a comment if you want a full video on how PCA uses these ideas. Thanks for watching and hope to see you in the next lesson. Bye for now.